Hello, this is Dylan Blair. Um, we are trying it for the fourth time now, so hopefully this one works. I'm going to segment it up into each individual component, so 9.1, 9.2, and 9.3, so you're going to have three lecture videos. Sorry, but I can't figure out another way around this. So for these sections that we're going over this week, we are going over vectors and all of the different vector topics that we could talk about. So vectors are a little bit more exciting for me because I am an engineer, and vectors are a type of mathematics that are very commonly used in all of the STEM fields. So your sciences, technologies, engineering, and mathematics. So for those of you going into STEM, make sure you pay close attention. Um, but yeah, so we are going to talk about what vectors are and how they're distinguishable from basic line segments. So yeah, we'll get to that. We'll talk about how we can add, subtract, and scale vectors analytically and graphically, how we write vectors in a vector notation, how we find the magnitude and the direction of a vector. We'll talk about what a unit vector is, and we'll also talk about principal unit vectors and how to decompose a vector into these principal unit vector notations. And then we will also talk about the dot product and also some applications of the dot product, such as projections of a vector onto another vector. So with that being said, our assignments, you need to make sure you are reading 9.1, 9.2, and 9.3. The homeworks for those are also open now. The homeworks from last week's content, so 8.3, 8.4, and 8.5 on complex numbers, are due this Thursday at midnight, so that's April 2nd. And then the homework for this content is due next Thursday, a day before the second exam. So that's April 9th at midnight. Another side note, all of the sections that are covered on this next exam, so 6.1 through 9.3, are going to be opened up at some time on Monday. I have a reminder to open them back up on Monday. So when I get to my computer, I'll open them back up. But they'll be opened up April 6th through April 9th at midnight, so the day before the exam. And then quiz 10 for this week, that's on Friday, April 3rd. It's due at midnight. I release it in the morning, but this quiz is more theoretical than normal, just because you guys do have the leisure of being able to look at your notes and your practice problems and such. And so I want to make sure that you guys actually understand the content rather than just simply knowing how to plug in numbers. So really do make sure you guys start the quiz much earlier than usual. Okay, and then as always, quizzes are submitted via Gradescope. Okay, so we're going to first talk about what a vector is. So a vector is a directed line segment. So that's a difference between a vector and a line segment, is we're directing this line segment. And we're only working in two-dimensional Cartesian coordinate systems in this class. So that's just your base x and y coordinates. And a vector possesses only magnitude and only direction. We don't care about the position. Okay, so I have three vectors drawn below. Oops. We have this vector right here, we have this vector right here, and we have this vector right here. Okay. Now these vectors are all identical, even though if we defined our coordinate system down here as x comma y, and say this is x naught, y naught, and this is x1, y1, and this is x2, y2. Even though they have different locations as to where they start, they're still the same vector because they have the same length. All three of these have the same length, and they have the same direction. Okay, so they all are pointing to the right by A and up by B. Right by A, up by B. Right by A, up by B. Okay. Now we denote a vector with a vector hat, and that's what I have drawn right here. Okay, so it's our variable v for a vector with a caret hat on top, or not a caret hat, a vector hat on top. And it's also common to see bold letter notations. That's going to be more common in text, so in textbooks and literature, which we have right here. When you see me write it, I'll always put the vector hat over the top because it's very difficult to draw bold letters clearly. And then to the right hand side of the equal sign, you have your horizontal component, which is this A. So that's saying that we are going to the right by A. And then we have our vertical component, which is B. So it's saying that we're going up by B. Okay. Now let's talk about how we can define a vector based off of 2 points. So this is assuming that, let's not do X. This is assuming that we have a vector v a comma b unknown. So we don't know that horizontal and the vertical component, but we do know the point at where the base of the vector starts and the point at where the head of the vector ends. Okay, and we denote that with a p that has x and y coordinate and a q that has x and y coordinate. Okay, so let's first look at the case that we're going from p to q. Okay, so we want the distance going to the right from x1 to x0. Okay, so in order to find that horizontal distance, in order to get this a to be positive, we want to take x1 minus x0, and that's going to give us that a distance. Okay, and then in order to find the distance, it's a positive distance going upward to give us this b, we need to take y1 minus y0, because that's going to give us a positive vertical distance b. Okay, now note vectors are the exact same no matter where we translate them. So we could have translated this vector, say, to right here, and it's still going to be the exact same vector. Okay, so what that means is that we could actually translate this vector so that the base of the vector is located at the origin. Now, when we look at the bottom right-hand side, what this is known as is a standard position of the vector, so that the base of the vector starts at the origin. Okay, this makes it very easy for us to conceptualize and perform a lot of calculations on vectors when we have it in its base or standard position, because we know the x-coordinate corresponds just to A and the y-coordinate corresponds just to B, rather than having these two x-coordinates and these two y-coordinates. Okay. Now, let's think about this on the contrary. What if we were to flip which point we started with and which point we ended with? So say we're starting with point Q and ending with point P. Okay. So we're effectively just flipping the direction by 180 degrees of the vector, right? We can see that visually from looking over here, from looking over here to looking over here. They're aligned exactly, just the head is at the different, at the opposite end. Okay. So now, in order to get this A direction to go to the left, we need A to be negative, and in order to get B to go down, we need B to be negative. So we need both A and B to be negative. Okay, so that means when we're taking the difference of these values, we want to take x0 minus x1, because x1 is larger in magnitude. So that means that when we're taking that distance, it's going to be pointing to the left, okay, which is effectively what we want it to do when we're in standard notation, or in the standard position, right? And then we'd similarly want to take y0 minus y1 so that we get this negative number that is pointing down. And similarly, standard position will also be negative. Okay. All right. Now let's talk about adding and scaling vectors. So doing some operations on these vectors. So Let's see. Okay, so we're going to assume that we have two vectors, a vector and a b vector. Let's assume that A has a horizontal component of A naught and a vertical component of A1, and B has a horizontal component of B naught and a vertical component of B1. Okay, so when we add vectors analytically, what this means is we're just adding them component-wise. So we're going to add the two horizontal components together, A naught and B naught, and we're going to add the two vertical components together, A1 and B1. Okay. Now let's think about what this means when we are doing it graphically. Okay. Actually, first, let's think about what b vector plus a vector is. Okay. Well, when we add those component-wise, we're going to have b naught plus a naught, comma, b1 plus a1. Okay. Well, b naught plus a naught is the exact same thing as a naught plus b naught because these are just scalar values. They're just real numbers. So let's say a naught was 1 and b naught was 2. 1 plus 2 is the exact same thing as 2 plus 1. They're both equal to 3. And this similar concept goes behind b1 and a1. Okay, so we know b plus a is equivalent to a plus b. Okay, and we're going to talk about that when we talk about graphically adding these as well, because there's a nice geometric representation of adding these vectors together. Okay, so we have a horizontal component of a naught, vertical component of a1, horizontal component of b naught, vertical component of b1. Okay. Now, when we add vectors together, we're going to take the first vector's head, and we're going to attach the tail of the second vector. Okay, so we're adding head to tail. Now, what this means is that we're going to take the result of the base of the original of the first vector to the head of the second vector. So we're basically following this path and finding that direct distance from that path. Okay. So now, if we were to do this b plus a, now our b is going to be down here, right? We've just translated the vector downward. And then our a vector is just translated to the right, so that we are now doing now we're doing head to tail for the head of the b vector and the tail of the a vector. Okay, so head to tail. And then we're taking that same resulting distance from the base to the very end along that path. And what we notice is we get this nice parallelogram. And that's a nice property that we get geometrically when we add vectors together. When we add two vectors together, when you switch the order of when you add them, it gives you this nice geometric property that they always create this parallelogram. Okay. Now let's talk about scaling. So now let's consider that same vector A, horizontal component, vertical component. Now we're going to consider a real number c. So this is not a vector, it's just a real number. It could be pi, it could be 81, it could be negative 500.267, it could be anything. Okay. So when we multiply or scale a vector a by the c, we are going to be multiplying that c to each of the components, so to both our horizontal and our vertical component. So now let's look at this geometrically. So a, we've assumed to be a naught and a1. Okay. Oh, and actually real quick, I forgot to talk about this. I did want to relate this analytical component back down to how we added these down here geometrically. Okay. Well, we knew that this length, this horizontal length, was a naught. And we knew that this longer length was b naught. And then in order to get to the top, we know that we went up by a1, and we went up this shorter length of b1. Okay, we don't think about adding vectors this way, but that is the exact same concept that we just did. We went to the right by a naught plus b naught, and we went up by a1 plus b1. Okay. So that's just to kind of relate to the analytical approach of adding them component-wise to how we did it, to what our result was for the graphical approach. Okay, so now back to the scalar component. So with this first one, we are considering C being equal to 2. So if we were to scale that 2 to each component, we would get 2 A naughts and 2 A1s. Okay, so that just means that we would be going, whoa, don't know what just happened there. We would be going A naught to the right twice and A1 up twice. Okay, so we just doubled its length. We just amplified the entire thing. Okay, so it's pointing in the exact same direction. It just has a double length and magnitude. Okay, so now let's consider if we were to do a negative number. So a negative number is just going to effectively flip everything, because when we scale each of the components, we're going to get negative A1 and negative A naught and negative A1. So that now we're going to be going to the left by A naught and down by A1. Okay, and that's how we add and scale vectors. And then subtracting is kind of a trivial component. It kind of follows the exact same thing, the exact same way as adding, but how we think of it is we're actually adding a scaled vector. So we're going to be taking A plus a -1 scaled vector B. So ultimately we'll be taking A1, A naught A1 plus negative B naught negative B1. Okay, and then that's when we add them component-wise so that we get A naught minus B naught and A1 minus B1. And this concept becomes more obvious when we actually do it graphically. Okay, now with magnitude and the angle of a vector. So we're supposing that we have some vector A again with an A naught horizontal, A1 vertical, and a vector has a magnitude that describes its length and an angle which describes its direction. Okay, so first with the magnitude, when we consider this vector down here, we can kind of envision that we can create this triangle, right? This right triangle. And it kind of goes back to our basis that we've been dealing with all semester. So that we have this right triangle that has this angle, this hypotenuse length, this base length, and this height. So using Pythagorean theorem, we can say the magnitude, and the magnitude is just denoted with these double brackets on both sides, okay, double straight line brackets on both sides. So we could say that that hypotenuse squared, which is our magnitude squared, is equal to A naught squared plus A1 squared. Okay, when you take the square root of both sides, we've now successfully solved for our magnitude using Pythagorean theorem. Okay, so this is synonymous to what we've been doing for the past month by finding the radius of a polar coordinate or finding the modulus of a complex number. Okay, now similarly, we want to relate everything that we know to the angle. Okay, so what we know is our horizontal component and our vertical component. So in order to relate those two to this angle, we can say that tangent of theta is equal to A1 over A naught, right? Which is opposite over adjacent, so ka toa. Okay, now this is just synonymous to finding the angle of a polar coordinate or finding an argument of a complex number. So it's the same thing that we've been doing for a little while now. It's just more practice essentially with a different context. Okay. Now what this means is that we can rewrite and decompose our vector A to its magnitude that's scaling some vector composed of angles. Okay. So what we can think of is, what we can think of is this cosine theta, sine theta. Okay, so we're going to just consider a smaller triangle. Let's actually change the color. We're going to consider this smaller triangle. Okay, and we're going to say its magnitude is 1. And the reason why we want its magnitude to be 1 is because then when we scale this new vector, so we're going to say that this is a vector right here, so that when we scale this new vector by its magnitude, it just expands it out by its magnitude so that we get back to our original vector. Now it sounds kind of silly that we're decomposing it this way, but it's actually very useful in later slides when we go over some proofs. Okay, but then we can define, say, a naught caret hat and an a1 caret hat, such that we can say theta is defined, is related to this a naught caret hat and a1 caret hat to be our horizontal and vertical components, right? And so we can say cosine of theta is equal to a naught caret hat over the hypotenuse, which is just 1. And we can say sine of theta is equal to a1 caret hat over 1, because that's the hypotenuse. And so we can say the horizontal component is just that cosine of theta, and this vertical component is that sine of theta. And its length is 1. Okay, so that means that when we scale it by its magnitude, we now get back to our original vector that we just had decomposed. Okay, and that is it for 9.1. I'm going to end this video and we'll pick back up on 9.2.